Hi, so welcome to the lab 6 video demo. So I've already swapped in the experiment. So if I go to the experiment, this is the NS file which we've used. We're using a 100 MB link and a 10 millisecond delay. This is the visualization. So let me log into the nodes. I've already logged into Ditter. So let me log into the node. This is node A and this is node B. Okay, so I want to show how TCP behaves when there is a large throughput, large loss and a large delay between the nodes. So let me go to the Data Lab website and give modify traffic shaping and let me give the delay as 200 millisecond and the loss to be 0.2 as mentioned in the lab. Say execute. Okay, so what I'll do now is create a file. I'll remove any file that is already there and I'll create a file of 1 gigabits. So this is the command for that. I create the file. It'll take some time and I'll transfer it to node B and let us see what throughput we are getting. So the file is created. So let me go to node B, remove any file that's already there. Okay, let us transfer the file. So this is the command. Let us see how much time it takes to transfer this file. So as you can see, the file transfer has started. You can see that the throughput is decreasing each second because of the link loss and the delay we have set. It's also showing stalled, which means that it's struggling to transfer even some bytes of data from node A to node B. It's continuously decreasing and you can see that it's reduced from megabytes per second to kilobytes per second. So I just want to give an idea that if we use a regular TCP, the throughput which we'll be getting is very low, and as the file size increases, this will be even more bad. So the aim of the experiment is to increase this throughput value and make the file transfer happen quickly and reliably. So to do that, we have to get into the TCP kernel code and modify some of the files so that the regular TCP procedure is not used and it uses our own custom TCP. So let me exit this and you can see that it will take days to transfer this file, and let me show you the kernel code and the changes which I have made. This is my local system where I've made all the changes. So let me get into lab6 and here as we have mentioned in the report in the appendix section, we are cloning the TCP kernel code from Git So the Torvalds is the creator of Linux. So we use his code, we download his code and make modifications there so that uh, the throughput is increased. So I've already done that, and if I'll directly, there'll be a folder called Linux that's created, and I'll directly log into that Linux folder. And now let me log into the folder, get into the folder where the real TCP codes are. So this is the folder. So if I give RT, here you can find all the TCP related codes such as timer.c, input.c, tcp.c, and hibla.c, and so on. So what I'll show you some changes which we have done in the code. So let me open tcp.c and search for lab6. And as you can see here, this is the function for retransmission, and what they were doing was they were left shifting the timeout variable. This is nothing but the timeout is equal to timeout by 2, so they're dividing by 2. So they were decreasing the uh, timeout value so that retransmissions occur frequently. So we have commented out that code in this file, and let me show you another file, tcp congestion.c, and let me see. As you can see here, the this is the slow start procedure, and this is what we have modified, which is modified for lab6 in comments. So you know that in TCP slow start, the congestion window is decreased to 1 as soon as congestion occurs, that is a packet loss occurs. So instead of decreasing it to 1, what we have done is we have set the congestion window to a congestion window clamp variable, which we set in the tcp.h file. So this is nothing but whenever a packet loss occurs, instead of decreasing the congestion window to 1, it will decrease it till the clamp variable, congestion window clamp, and again the TCP process will begin from there. So this modification is done in the slow start procedure. Let me show you one more file, that is TCP hibla, which we have used. We can use any file which we want. We can use TCP Vegas or TCP Vino or TCP BBR, but we are using the hibla, TCP hibla version. So here we make changes here. So again here, the slow start command window, we are set the congestion window. So the congestion window, we are setting it to the clamp variable. So we have modified around 8 to 9 files, and this is the procedure which we have followed. So in many files the congestion window is set to 1. We have removed that, and let me show you another file, that is tcp timer.c lab6. So here we have removed the if and else condition, which will take a lot of time. This is if an acknowledgement is missed, uh, this procedure is executed, and this is gonna consume a lot of time, thereby decreasing the throughput. So we've commented all this. So we've gone about it in this way. Let me show you the tcp.h file that is in this folder, include and net. We have the tcp.h file here. So lab6 again. See, this is the change we have done here. So usually in TCP, after 3 duplicate acknowledgements are received at the sender, the retransmission is done. But we are setting it this value to be 1, so that whenever just one duplicate acknowledgement occurs, we are saying that transmit the file again. So this will save a lot of time, in the sense that the sender doesn't have to wait for 3 duplicate acknowledgements for the receiver to send, thereby increasing the throughput. So, and again, here we have increased the congestion window size. This was, we have set it to maximum. So this is the initial congestion window size. So if this is low, the number of packets sent out at the first try will be low. So we have set this to a maximum value, so that maximum number of packets are sent. So like this, we have modified around 8 to 9 files. So this is the only header file which we are modifying. So let me go back and to the appendix part here. After we made changes, we are executing all these commands, and finally this is the command which will execute, which will give us the .deb files, which will have the Linux image and the Linux headers of the kernel. So we can name this anything. I've named it as lab6 modified. So after the .deb files are generated, we'll send it to ditter, send it to the ditter node A, and install it there, so that it can use our kernel instead of the original TCP kernel. So this process which I mentioned here will take a lot of time. It took us around 5 to 6 hours to get built. So I'm just gonna show you the .deb files which we have got after executing that command. Go back, and these are the .deb files which were generated. So we'll be needing these two DB files which we need to send to the sender. So we'll be using SCP to transfer this. So let me show you an example. We'll give SCP. Let me copy this, paste. So this one, Linux headers, lab modified. We'll give our username at users.isi.ditlab.net, and the place where it should go. So if I minimize this, I can show you. So this is the SCP command. We'll transfer both headers file and image file using that SCP command. So once we do that, let me clear out this. So if I go to lab6, you can see that these files have been transferred to our data system. So before I install the kernel here, I want to show you that which version of kernel the node A is using. So you can see that some 4.4.083 generic kernel version is being used for as of now. So let me install these two files and show you how it uses our kernel. So the command to install this is sudo dpkg -i. Let us install the header file first. So it's installing. So it's installed. Now it's time to install the image file. So again, same command. So ignore these errors. Let me clear, and I'll give a sudo reboot. So the connection to node A is lost now. So as I was telling you, if I refresh this now, it's shut down. So it'll take a couple of minutes to boot up. So let's wait for that. Only after it. So finally, it's showing that node A is up. So now we can log into node A again. So it's successfully logged in. Clear it, and first let me ping node B to show you that the RTT it's taking is 400 milliseconds. So let me fit this. So there is some packet loss, and since the delay is 200, the RTT is 400. Let me clear this. So now if I give uname -a, as you can see, this is our kernel. This was the name which we gave. This has been installed successfully. So if this is corrupted or it's not proper, the node will never boot up. So the node A booted up successfully. The compilation of the kernel is successful. So now let us create one more file. Let us remove the old file. And let us transfer the 1 GB file and see if there is any throughput improvement from our kernel. So this is the command to create a 1 GB file. Let me place it here. Let me remove it from node B as well. Okay. So let me clear it and let me go to node A, clear this as well, and I'll give the scp command. So the transfer has started, and as you can see that the throughput is not decreasing as we saw when we used our first TCP module. That's the original module. So this process is going to take around 12 to 13 minutes as it's showing. So I'm going to edit out the part where this transfer happens, and I'm going to show you the final throughput and the MD5 sum on both the sender and the client. Now we can see that the file transfer has completed, and it just took 13 minutes, and the throughput is 1.3 megabytes per second, which we have to multiply with 8 to convert it to bits per second, and this will come up to around 10.5 megabits per second. So as the last step for this lab6 demo, let me check the MD5 sum on both sides. So it's MD5 sum, then data.bin. So this is the MD file which we got. Let me check it here. So as you can see that the MD file matches. So we have successfully transferred the file using our kernel, and we've increased the throughput, and the file transfer is also reliable. So that's it for this experiment. Thank you.